As you can see, our topic tonight is distant starlight. Does it disprove biblical creation? Now, creation talks come in several different kinds. Some are proclaiming the wonder of what the Lord has made. Others are answering attacks from critics. And there's a few other flavors of creation talk as well. Tonight's talk is actually a mixture of a couple of those. On the one hand, we're going to answer a common attack from critics. And at the same time, we're going to turn that around and show that they're actually vulnerable to it, whereas we are not. Now, you may have heard of the distant starlight problem. And here's basically what it's about. We see light from distant objects, objects that are very far away. So how does the light get here? Well, it travels through space. Does that process take some time? Yes, apparently it does. Can we calculate how long these beams of light take to get here? Well, it would seem so. And it would also seem that some of these beams of light that we see take an awful long time to get here. In fact, we see things that are so far away that light would need millions or even billions of years to get here. So that would seem to pose a problem then for a straightforward interpretation of what the Bible has to say about creation, that the earth and by extension the universe is only a matter of thousands of years old. Not millions, not billions, just thousands. And the calculation for this issue goes something like this. We can calculate the time that light would take to get here by dividing the distance by the speed. And indeed, we see some things that apparently, according to that calculation, would need much longer than that period for the light to get here. For example, the Andromeda galaxy is about 2.5 million light years away. And a light year is actually a unit of distance. It's the amount of the distance over which light would travel in 1 year. So if the Andromeda galaxy is 2.5 million light years away, then that would, so it would seem, indicate that the light needed 2.5 million years to get here. And in fact, we see things even further away than that, much, much further away, out to billions of light years away. Again, indicating billions of years for the time to get here. And this is seemingly a very straightforward argument, isn't it? And as a result, and because it seems so instantly fatal to a creationist viewpoint, of course the atheists have lots of discussions about this. This is a page from the Rational Wiki, which is of course an atheist site. And you can see there's, by the number of topics in the table of contents, there's a lot of discussion about this. This is one of their favorite arguments. In fact, it's not only among atheists that it is thought that this discredits a straightforward view of biblical creation. Even some Christians do not accept straightforward interpretation of Genesis because of this issue. For example, Dr. Norman Geisler said this: "I think the speed of light is the crucial thing. If you could prove that the speed of light changes, you'd probably convert me to a young earth creationist." Dr. Geisler is not a young earth creationist now. Now, he's a brilliant scholar, a brilliant apologist, a brilliant defender of the Christian faith, and has done that very good work in that area for decades. Yet, on this one issue, he does not agree with probably most of us in this room that Genesis is actual history and should be interpreted straightforwardly as what the text would say. He believes in an old earth. Why? Well, according to this quote, this speed of light issue, the time travel issue, is a major sticking point for him. And he's not alone in this. William Lane Craig, again, a brilliant defender of the Christian faith, debates atheists and unbelievers of all sorts, brilliant apologist. But on this one issue, he does not agree with us that Genesis should be read straightforwardly, indicating that the earth is young. Why? Because, as he says, quote, "The scientific evidence overwhelmingly supports the idea that the earth is very ancient. When you think that we can see the stars, that very simple fact that you can see these stars billions of light years away shows how ancient the universe is." Now, many people immediately focus on these objects that would supposedly take millions or billions of years to get here. Actually, the problem isn't even to that scale. The problem actually applies over a shorter time span as well. For example, when Adam woke up on day 6 of creation week there in the garden, could he see any stars at all? Well, the closest one to us is Proxima Centauri. That's over 4 light years away from us. So did Adam have to wait over 4 years to see his first star? Now, I wouldn't think so. It seems to me that Genesis implies Adam was able to see stars right away. So therefore, there's this light travel issue is not merely for the things way far out there, is it? It's even for the things closer in. If you're going to accept Genesis as it's written, then you have to grapple with this light travel time problem. And this is how I'll refer to this issue for the remainder of my talk here. When you hear me talk about the LTT issue, that's what I'm talking about. How long did how long did light take to travel from there to here? Now here's why this all matters. You can calculate fairly straightforwardly from Scripture that Adam was created roughly 6,000 years ago. You can do that by adding up all the genealogies and so on. Well, the Bible doesn't tell us a specific date for the creation of the earth or the universe, but it does say that those creation events happened right before Adam was created. So if Adam was created 6,000 years ago, then that would put the earth and the cosmos itself at basically that age as well. As Genesis 1 says, God created man in his own image. In the image of God created he him, male and female created he them. And God saw everything that he had made, and behold, it was very good. And the evening and the morning were the sixth day. Genesis is written in the language that indicates these are straightforward days of creation. You can't say each day was in this indefinite period of time requiring millions or billions of years, whatever. That's not how it's written. In the beginning, God created the heavens and the earth. Okay, so in the very beginning, the heavens and the earth were created. How does that relate to when Adam was created? Well, over in Mark 10, Jesus said something to some of his critics who were challenging him about divorce. They said, Moses permitted a man to write a certificate of dismissal and to divorce her. But Jesus said to them, he wrote this commandment for you because of your hard hearts. Okay, now here's the relevant part to our talk tonight. Jesus said, at the beginning of creation, God made them male and female. Now, Jesus is talking here about the question of whether or not divorce is allowable. He's referring to the fact that God made Adam and Eve and made them from the very beginning of creation as a couple. Therefore, marriage is God's plan. Divorce is not part of God's plan. But this is relevant to our issue here tonight because he affirms that Adam and Eve were made male and female from the beginning of creation, not 13.8 billion years after a Big Bang. Heavens and earth were made right before Adam and Eve were. And since Adam is 6,000 years ago, more or less, that would put the earth and that would put the cosmos itself at 6,000 years, give or take, according to what the Bible says. So the atheist would therefore say, well, thank you for confirming that, because that means the Bible has been disproved by this LTT issue. Moreover, the light travel time that's billions of years required, that works perfectly well with the Big Bang, but it disproves the Bible. So this is a great argument for my side, so says the atheist. But that's not actually true. This seems like a straightforward argument, but as we'll talk about this evening, it is not actually a straightforward argument. That's because it requires and includes a lot of assumptions. Can you spot these assumptions? I mean, this seems like a pretty straightforward calculation, doesn't it? I mean, you can't really get much simpler, can you? Nevertheless, there are assumptions in here. For example, this calculation includes the speed of light. And it includes the assumption that the speed of light has never changed through history. So some people have focused on this previously and said, you know, if the speed of light used to be higher in the past, that would solve this whole problem, wouldn't it? Because if light used to travel much more quickly in the past, then it would require much less time for the light to get here from out there. Therefore, this problem goes away. Now, is this a good solution to the LTT issue? Well, it seemed promising for a while, but most creationists no longer are interested in this as a valid solution. It's been scrutinized and found to be wanting by most people who used to be interested in it previously. There are still a few looking into it, but the broader creation community is no longer interested in this as a solution, I'll say. It's important to mention here, though, for a couple of reasons. Number one, a lot of people have heard about this and wonder if it's still a valid solution. But number two, it's a good illustration as to how important these assumptions are. I mean, it's pretty clear, I hope, that the assumption of an unchanging speed is built into this seemingly simple calculation, right? So even though this particular assumption seems to be a reasonable one, does that then leave us with no answer to the LTT issue? No, not at all, because there's a lot more assumptions built into that equation as well. I'm going to focus tonight on 7 assumptions, and there's actually quite a few more than this. But in our time tonight, we'll limit ourselves just to these. I will list them. Actually, let me back up a minute. These are assumptions made by the people posing the LTT issue as a challenge to biblical veracity, biblical truth. So I'll list the assumptions first, all in one list here, and then I'll go through them individually for the remainder of our time tonight. Assumption number 1 is usually something made by the person making the challenge to you. He assumes that the Big Bang is consistent with the universe and biblical creation is not. He assumes that the Big Bang is consistent with the LTT issue itself and that biblical creation is not. He assumes that we know light's one-way speed in order to make that calculation. He assumes that the speed of light is constant through space. He assumes that light actually traveled the entire distance to get here from there. He's assuming the light always traveled all through history as it's doing today. And lastly, he assumes that the universe has no center of mass. Now, some of those may have made sense to you. I'm assuming probably some of them may be a bit of a head-scratcher. But let's talk about each of these now in turn. Assumption number 1 is that the Big Bang is consistent with the universe and biblical creation is not. Well, those of you who have seen me speak here before have probably heard me talk about some of this stuff already, so I'm just going to briefly skim this issue. But indeed, we can actually spend more than one presentation just showing all the ways in which the Big Bang actually is not consistent with the universe in which we live. The idea that there was initially nothing and then the universe leapt into existence from the void, and from that formed all the various things we see today. That's the basic idea behind the Big Bang model. Ask a secular cosmologist, why do you believe the Big Bang model? What evidence is there for it? Well, he will tell you about several things. He will tell you that there's redshifts on a large enough distance, every distance scale, I should say, everywhere in the universe. And this supports the idea that the Big Bang happened. What is a redshift? Well, you may be familiar with the idea that if you shine sunlight through a prism, it'll break it up into all the various colors that it contains. Astronomers use instruments called spectrometers to do basically that same thing. Here is sunlight having been broken up into its different wavelengths, its different colors, through a spectrometer. Notice that all the colors that the human eye can see are represented here, except for a few that are missing, those little black lines. Those are called absorption lines, and they are the result of sunlight having specific wavelengths absorbed by elements in the sun's atmosphere on its way to us. And we can actually tell what elements are in the sun's atmosphere by analyzing the sets of lines that we see. Now here's a separate spectral pattern from a supercluster of galaxies far away from us. Notice how they have basically the same absorption lines as the sun does, which tells us that these distant stars are made up of basically the same stuff that the sun is. But notice also that that pattern is shifted over to the red end of the spectrum. Thus it's called a red shift. What is causing this red shift? Well, red shifts can be caused when a light source, a light emitting source, is moving away from you. You can think of the light being stretched out in a sense as it moves. Conversely, if the light source is moving towards you, light will be blue shifted. You can think of that as the light being sort of bunched up. So by analyzing the light from distant objects, then, we can tell how its relative motion is compared to us. If the light is red shifted, the object's moving away. If it's blue shifted, it's moving toward us. And there are a few objects close by to us that are blue shifted, so they're apparently moving toward us. But everything else we see in every direction we look is red shifted. And the farther out we look, the more red shifted these objects become. This is actually the fundamental discovery that began, if you will, that served as the foundation of the Big Bang model. The basic idea is this. If we are in this plane here, the second one from the top, and this is the current situation today, we're in one of these galaxies looking at the others, well, if they're moving away from us over time, then in the future, we'll be in this situation like this top diagram, where everything has moved farther away from us compared to what it is today. Now let's go back to today. Think about what it looked like backwards in time then. If everything is moving away from everything else today, that means in the past, everything used to be closer together. Go back far enough in time and you reach a point in time when the entire universe was at the same place. That's the basic idea behind the Big Bang model. That the redshifts indicate that the universe is expanding today, which means it used to be much smaller in the past, Run that mental movie backwards far enough, and you reach a time when the Big Bang itself had the entire universe at a point total. So, second item that the secular cosmologist will quote to you is that the Big Bang model has been tweaked to consistently reflect the ratios of various light elements in the universe today, hydrogen, helium, and so on. And he will tell you, thirdly, that the cosmic microwave background is great evidence for the Big Bang. What is the cosmic microwave background? Well, I'm showing you a sky map here where the different colors within it represent different temperatures of radiation coming to Earth from all points in space. And if you're not familiar with the sky map, this is basically how one of these is generated. This little animation shows us inside of a galaxy. The Milky Way doesn't really quite look like that, but whatever. So from our perspective, we see stars and things in all various directions. Now, if you sort of model that like it was a sphere surrounding the Earth, and then you unwrap that sphere, that gives you a sky map. So this is a sky map showing that there's microwave radiation coming to Earth from all directions in space. This is thought to be the afterglow of the Big Bang itself. The model actually predicted that this would be found, and when it was found in the mid-60s, this was viewed as the final proof, the conclusive proof, that the Big Bang was correct. And actually, other secular cosmologies at the time were abandoned, and the Big Bang has reigned as the dominant model among secular cosmologists ever since. So you will be told, if you ask about this, that these three lines of evidence prove that the Big Bang happened. We see redshifts in all directions, indicating an expanding universe. We see an abundance of light elements that's consistent with the Big Bang model, and we see the afterglow from the Big Bang itself in all directions in space. But is this actually proof for the Big Bang? Well, no, these items are not, because it turns out they're consistent with other cosmogonies as well. Cosmogony means history of the universe. So if they're consistent with the Big Bang model, but also consistent with other cosmogonies too, then you can't say that it proves the Big Bang model to the exclusion of anything else, can you? Nor, by the way, are these all that consistent with the Big Bang anymore anyway, especially the CMB, cosmic microwave background. As we've learned more about it, it is causing problems for the Big Bang. And I'm just kind of skimming this topic here for the benefit of, well, time. And also I know that some of you have heard of these items before. But just to make the point, the Big Bang is actually less consistent with the universe than it is claimed. In fact, it is very inconsistent with the universe in a lot of important ways. For example, the universe operates according to physics. And the Big Bang model has some real problems with physics. Big Bang model says that in the beginning, there was nothing. And then it exploded. What exploded? Well, nothing exploded. How can nothing explode? How can you go from nothing to everything? Well, nothing can explode and did explode. That's why there's everything rather than nothing. Or so we are told. But does this really make sense? Can nothing actually create everything? No, nothing can create nothing. Nothing can do nothing. From nothing, nothing comes. As R.C. Sproul once said, if there were ever once truly nothing, there never once could be anything. Which is really profound if you think about it. And the whole idea of the universe coming into existence, popping into existence from nothing, actually runs head-on into some very fundamental laws of physics. For example, the conservation of matter and energy is probably the most fundamental idea in physics. If you take a physics class, you will be taught one part of this law right away, and a lot of the work you do in a physics class is actually based on this idea. It's called the first law of thermodynamics. It says that all the matter and energy in the universe, its sum total, is conserved. It never changes. Now, you can change the relative amounts of matter and energy as long as the sum total never changes. What do I mean by change the relative amounts? Well, physics now understands that matter and energy are equivalent. They're different forms of the same thing. You may be familiar with the equation E equals mc squared. E equals energy, m equals mass, the amount of stuff or matter you have, and then c is the speed of light, which is a large number. So that tells you a little bit of stuff can be converted into a lot of energy. And the most efficient way we know how to do that is in a nuclear explosion. Again, a little bit of stuff converts into a lot of energy. We can go the opposite direction too, and convert a lot of energy into a little bit of stuff. We do that in particle accelerators. Little chunks of matter go zipping around at close to the speed of light and get smashed together. Now, more material comes out of these collisions than went in. Does that mean we created something from nothing? No. All we did was we converted the kinetic energy of the particles, the energy of motion going around, and converted that into matter. But we didn't actually create matter from nothing. We had to have the energy first to then convert into the matter. So this is a very fundamental idea in physics. You can't create energy or matter from nothing. You have to have the other version of it to convert it into. And we see this principle in our lives every day. Why do you need to eat food every day? Regardless of how difficult that process might sometimes be. Because your body needs energy, can't make it from nothing because that would violate physics, so you have to get it from the chemical energy stored in the food. Of course, you have to get it in your mouth first, but that's a different story. Why do you get a bill from the power company every month? Because your appliances need energy to run, can't make energy from nothing because that would violate physics, so it needs to get it from the power company, which also can't make it from nothing because that would violate physics. Has to get it from the chemical energy in coal, or the gravitational potential energy in flowing water, or the energy from the sun, which also can't make its energy from nothing because that would violate physics. It has to burn hydrogen or helium to get it, and so on. So this principle is very fundamental to how the universe works. In fact, you couldn't be watching this presentation tonight if this principle weren't true, because some of the principles of electronic circuit design are based on this principle being true. If you ever take a physics class and you solve a homework problem or a test question or whatever in such a way that it violates this principle, your answer is automatically wrong, because that's how fundamental this is to physics. Yet the Big Bang violates this on the largest possible scale, if you think about it. It says all the energy and matter in the entire universe popped into existence from nothing. Now, secular folks will say that, yeah, this seems to be a problem for us, but it's not really a problem because the Big Bang, yes, everything had to come from nothing, but actually it doesn't violate this principle because everything is really nothing. So the Big Bang on a net basis didn't actually create anything. Now, this doesn't actually work. I hear some chuckles. They have what they think is a sophisticated explanation as to how they can justify that. That explanation doesn't actually work. I can share with you after the talk tonight if you're curious about details of that. For the sake of time, though, I'm going to move on for now. Some people do recognize that the universe coming from nothing would be a problem for them, though. So they say, okay, in the beginning, there was a quantum field in the vacuum. The Big Bang didn't actually come from the void, from nothing, truly nothing. There was this vacuum of space with a quantum field in it, and that's how the universe popped into existence. Well, have you really explained anything by invoking a vacuum of space that had a quantum fluctuation in it? Well, where did the vacuum of space come from? Because that itself is something according to physics. So you haven't really explained where ultimate reality came from then, have you? Where did the vacuum of space come from? Did it have its origin in nothing? If so, then you have the same problem just further back. Because indeed, a vacuum of space is something, as this secular cosmologist says. A more fundamental problem is that this scenario, the universe popping into existence from a vacuum, does not really explain the origin of the universe. Quantum fluctuation of the vacuum assumes that there was a vacuum of some pre-existing space, and we now know that vacuum is very different from nothing. Vacuum, or empty space, has energy and tension. It can bend and warp, so it is unquestionably something. Alan Guth, a very prominent cosmologist, said this: from the point of view of general relativity, empty space is unambiguously something. According to general relativity, space is not a passive background, but instead a flexible medium that can bend, twist, and flex. A proposal that the universe was created from empty space seems no more fundamental than a proposal that the universe was spawned by a piece of rubber. It might be true, but one would still want to ask where the piece of rubber came from. So you see the problem. If you say that the universe came from nothing, then you're violating the conservation of energy and matter, which is, again, probably the most fundamental principle in physics. If you say, well, it popped into existence from a vacuum of space, well, that too is something, so where did that something come from? If you're saying it too at one point had to have an origin, then you have the same problem just further back. So the only real way to get out of this trap is to say that in the beginning there was an eternal vacuum that had the ability to make quantum fluctuations. There's always been something, in other words. So that does indeed get you out of the trap of violating the conservation of matter and energy, but it instead raises a separate problem for you, which is that you're now violating the second law of thermodynamics instead of the first. What is the second law of thermodynamics? Well, you may have heard it expressed as the idea that entropy will always increase. And for a concrete example of this, I like to use coffee, because coffee is awesome, because I love coffee. So if you take a cup of hot coffee and put it on the counter, and you don't drink it and no one else does, what does it do? It cools off. Why does it cool off? More specifically, where does the energy go? Does the energy just vanish? No. The energy flows out of the cup and into the room, right? So the coffee gets cooler, the room heats up slightly, and then those two processes meet at a new temperature that everything is at. So second law of thermodynamics tells us that hot things will cool off until the energy is evenly spaced. If you have a concentration of energy like that, it will eventually dissipate until it's evenly distributed. That's what is meant by entropy will always increase. Okay, so if you walk into a room and you see a hot cup of coffee on the counter, how long has it been there? A long time or short time? Has to be a short time. Well, how do you know that? Because if it were a long time, it would have already have cooled off, right? Could a hot cup of coffee have been there eternally long for an infinite amount of time? Obviously not. If it had been there infinitely long, it would have cooled off an infinite amount of time ago. So why am I talking about coffee? Because this is a good analogy for other things we see in the universe. We can use this principle that that concentrations of energy will dissipate. We can use that as a sort of clock to tell us how old something is. Do we see anything in the universe now that hasn't cooled off yet? We see lots of things, like stars, for example. Stars are very hot objects existing in very cold space. Now, after a certain amount of time has passed, every star will eventually burn out or explode or whatever. It'll go away somehow. At that point, it's no longer a star, right? So if the universe were eternally old, would we see stars anymore? No, they'd have cooled off infinitely long ago. Now, some people would say, well, yeah, but new ones can form. Well, star formation also requires energy, of which there's a finite amount. So if the universe were infinitely old, then star formation also would have ceased infinitely long ago, and we wouldn't see any of this going on today. So the fact that stars are still there tells us what? Tells us that the universe can't be eternal. And that same reasoning can apply toward a vacuum of space existing before the Big Bang happened, because all of reality, if physics has to apply to everything we see, all of reality can't be eternal either. Because if all of reality were infinitely old, it would no longer have any energy left to be able to make our universe in this Big Bang. So you see the problem then. Atheistic cosmogonies are caught in a trap, really. If you're going to be an atheist, come up with an origins model for everything, you have to pick which fundamental part of physics you want to violate. If you're going to say everything came from nothing, you're violating the first law of thermodynamics. If you're saying it's very old and there's always been something, well, now you're violating the second. Because the first law says the universe can't have had a beginning, therefore it must be eternal. The second law says it can't be eternal, therefore it must have had a beginning. So, if you're going to be a secular cosmologist, you have to pick which of those two fundamental parts of physics you're going to deny. There's a lot more we could say about whether or not the Big Bang is consistent with the universe. That's just a short summary. And for those of you who saw that already on my DVD or one of my previous presentations, thanks for hanging in there. Because now we're going to move on to some material you haven't seen before. Assumption number 2, made by the person challenging the Bible with the LTT issue, is that the Big Bang doesn't have an LTT issue of its own. Turns out, though, that it does. I mentioned earlier that the CMB, cosmic microwave background, is thought to be this afterglow of the Big Bang. The thing is, though, this turns out to be a large problem for the Big Bang in some important ways. Now, some of them are very specific to the Big Bang model itself. I'm not going to cover those now. But the fact that the entire universe is the same temperature to a very high degree of precision causes a real problem for the Big Bang model. In a sense, a light travel time problem for the Big Bang model itself. Why is that? Well, because let's say we are looking in opposite directions in space. So over on the left, we see a galaxy that's, say, 10 billion light years away. Now, according to the LTT way of looking at things, the light took 10 billion years to get here. On the other side, the opposite side of the universe from us, we see another object, also 10 billion light years away. Now, how long would it take light to get from one side of the universe clear to the other side in this little drawing here? Well, it would take 20 billion years, right? Because we're in the middle. But the universe itself is only supposed to be less than 14 billion. Turns out that the universe being at the same temperature everywhere doesn't work with the Big Bang model, because there literally has not been enough time for light, and therefore anything else like heat energy, to travel from one side of the universe all the way over to the other side. And if opposite sides of the universe have not been able to exchange energy yet, they shouldn't be at the same temperature. But they are at the same temperature. The entire universe, all directions that we look, is very even in this regard. Big Bang model says that cannot be. There has not yet been enough time for the universe to come into thermal equilibrium like this. But it is at equilibrium. Are secular cosmologists aware of this? Yes, they are. They tried to explain it by invoking a period of inflation right after the Big Bang happened. Inflation is the idea that right after the Big Bang happened and the universe popped into existence, it spontaneously inflated at multiple times the speed of light for a very short period of time. Now, this would solve the LTT issue for the Big Bang, but it raises a separate question. What is this magical process of inflation? Do we see it inside of physics? No, we don't. The particle that supposedly does all this, called the inflaton, is completely outside of known physics. It's never been seen anywhere. Nor is there room for this particle within the standard model of physics. As this author admitted, what drove inflation? Well, nobody knows. Physicists have suggested different models to describe the inflating universe, but all the solutions are mathematical conveniences with no particular physical basis. In other words, people are writing equations saying, this is what the universe needs to have done in the past in order to prevent the Big Bang model from being disproven by the facts. But that's just writing an equation. That has nothing to do with what is actually possible. All the theories of inflation amount to proof that we don't have one good theory yet, says this astrophysicist. And as this secular cosmologist admits, inflation's theoretical underpinnings may be rather tentative. The inflaton, after all, is a hypothetical field. In other words, it's something we made up, not something we've observed, whose existence has yet to be demonstrated. And he goes on. Moreover, as we've studied the CMB and gotten more precise measurements of it, inflation looks less and less possible anyway. Not that, I've already said that such a thing is impossible and it's outside of physics, but even according to the expectations of people who believe in this, the data are not conforming to what they expected. This author here, I should say this is actually a multiple author paper, but these authors here talk about how the models most favored by the data, combined with early results, suffer from exacerbated forms of initial conditions and multiverse problems, and they create a new difficulty that we call the inflationary unlikeliness problem. That is, the favored or necessary inflaton potentials are exponentially unlikely, according to the logic of the inflationary paradigm itself. This is interesting because this paper, which is criticizing the idea that inflation never happened, is actually written by a person who was one of the original authors of inflationary theory. One of the people who came up with this idea in the first place is now rejecting it because he says it's exponentially unlikely according to its own logic. So what do we call a process that relies on something that's outside of physics, for which there's no room within physics, that's never been seen, and that's exponentially unlikely according to its own logic? Well, we call that a miracle. So secular cosmologists are trying to solve the Big Bang's LTT problem of its own by invoking a miracle. So this assumption that the typical LTT challenger is making, then, isn't correct. He thinks that he's on solid ground, and from that solid ground, he can attack the idea of biblical creation. No, he has an LTT problem of his own that he has to explain if he's going to even talk about this in the first place. Okay, the remaining 5 assumptions of the 7 that we'll talk about this evening are less about the Big Bang model and more about the actual issue itself. For example, this calculation assumes that we know light's one-way speed. Remember the little calculation that we're talking about here. Obviously, the speed of light is referring to the speed from out there to here. Notice that's a one-way speed. It starts out there and it stops here. Why is that important? Because we know light's two-way speed when it goes out to somewhere and comes back. I'll talk about that in a minute. But we don't know its one-way speed. In fact, it turns out it's actually impossible to know its one-way speed. Who's heard of Jason Lyle's anisotropic synchrony convention? Anybody? A few hands. Now we know who the real creation geeks are in the room. Right. That's what we're going to talk about here next. For those of you who didn't know what that was, that's fine. This idea actually comes out of Albert Einstein's theory of relativity. Einstein himself said it is impossible to know the one-way speed of light. You can only ever know the two-way. Why is that? Well, let's talk about this for a minute. This is a photograph of Usain Bolt in 2008 in the Olympics in China, setting a world record for the 100-meter dash. He did it in 9.69 seconds, which is pretty amazing. And then he subsequently broke his own record again later in a different race. Okay, but in this particular race, he ran it in 9.69 seconds. Where's the clock that measured that time? That's the finish line, right? I mean, that makes sense. And they actually have some fairly sophisticated ways now with all these electronic gadgets to measure exactly when a part of someone's body breaks the finish line for the first time. Now, how do they know when to start the clock? Because if the clock is at the finish line, well, the runners start at the starting line, which is a different place. How do they know when to start the clock at the finish line to measure the final time of the race? Well, they used to do the business where some guy stood at the line and fired a pistol, and then someone at the finish line would start a stopwatch. Now, obviously, that's not precise enough when you have to measure things, as you do today, to 1/100th of a second. So now it's done electronically. Now they have a signal to start the race. My understanding is it's actually a recording now of a starter pistol. I say my understanding because I know it's a surprise, but I know I had the body of an Olympic runner, but I actually don't run so I've never actually participated in one of these myself. But they play a recording of the starting pistol, and then the electronic signal travels to this clock here, and when this clock at the finish line receives the signal, that's when it starts measuring time. So you could actually argue that this time here, 9.69 seconds, is actually not fully accurate because it doesn't include that brief fraction of a second when the race had begun, but the signal had not yet reached that clock at the finish line. But for 100 meters, and since the signal travels at the speed of light, that little brief instant of time is irrelevant. I mean, it doesn't matter for practical purposes. Okay, so this all works fine. This whole system works fine as long as you're measuring something like a human running. What if you wanted to measure the one-way speed of light itself? How would you do that? Well, if you had the light beam start at the starting line and then fire toward the finish line, well, your clock at the finish line has to know when to start ticking to measure the time, right? But if the signal that goes from the starting line to the finish line to tell the clock to start, if that signal travels at the speed of light, it's traveling at the same speed the light beam itself is, right? So your clock will be told to start exactly at the time that the light beam you're trying to measure arrives. So obviously this situation isn't going to work, right? If you're going to measure the one-way speed of light, you can't have separate clocks where there's a signal sent from clock A to clock B, can you? There's no way to do that. Okay, so we have to do it a different way. Let's think of that different way. What if, before the race, we measured out exactly, to the finest degree we can, the exact middle point between the start line and the finish line? And we agreed put a device right in between that we agree then that we're going to fire this thing and the signal is going to travel in both directions at the same time. And since those two distances are equal, we know that the signal will get to both clocks exactly at the same time. That seems to be a way around this problem, right? Then when clock A starts, or more accurately when the light beam itself is begun, clock B knows exactly when that starting event happened, because it will start its time measurement exactly at that time. Or will it? What are you assuming here? You're assuming that the speed of light, that the one-way speed of light from the middle to clock B and from the middle down to clock A at the starting line, you're assuming that the one-way speed of light is the same in both directions, aren't you? But that's one of the things you're trying to prove, one of the things you're trying to measure here. So obviously you can't assume something if you're trying to prove it, right? That's invalid logic. So turns out that if you're going to have separate clocks, you can't measure the one-way speed of light. But wait a minute, someone will say. Here's plan C, a third way to do this. We'll put both clocks in the same place. We'll synchronize them precisely. And then we'll decide on a time. Let's say we synchronize the clocks at noon, and we agree that at 2 p.m. exactly, the race will start. So we synchronize the clocks, maybe at the starting line, and then move the clock one of the clocks down to the finish line, and then at exactly 2 p.m., that's when the race will happen. That's how we know when to start the second clock. That seems like a good plan, except for one problem. Relativity says that when you move something, time changes for it slightly. So the clocks can be perfectly synchronized at the starting line, but as soon as you try to move the second clock down to the finish line, you've moved them out of synchronization again. So this doesn't work either. Turns out you can never measure the one-way speed of light using two clocks like this. The only way you can ever measure the speed of light is to use one clock, which means you have to fire light off in one direction, bounce it off something like a mirror, and then see how long it takes to come back to you. Since in this case you're using the same clock to start the race and to stop the race, now you can successfully measure this. So a two-way speed of light is the only way you can ever measure light. You can never, even in theory, measure it in only one direction, because you can't start with separated clocks, nor can you start with the clocks together. Ultimately, it's impossible, even in theory, to measure the one-way speed of light, because you can only ever measure its two-way speed. Einstein himself admitted this is true. And here's why I'm spending the time to talk about this tonight. Einstein admitted that if you're going to have this experiment where light is traveling in only one direction, since you can never measure that, it's meaningless to say that it's a specific number. He said we're actually free to choose the value that you want in your experiment. Travel time is not a supposition nor a hypothesis about the physical nature of light. It's a stipulation. Any experiment you can do where there's a one-way speed of light involved, you're free to choose the one-way speed that you want. Now, in most situations, people tend to assume that the one-way speed is the same as the two-way speed. But that's an assumption. It's a choice, as Einstein made clear. You're free to choose whichever one you want. So you say, wait a minute, though. So let's talk more about the stars again. You're free to, since this is a one-way incoming speed of light, you're free to say it's infinitely fast on the way in. That works according to Einstein. Now, if the light is infinitely fast coming in, that does away with the whole light travel time issue, doesn't it? Because the light takes 0 seconds to get here. You say, well, that doesn't make sense, though. Well, it makes sense as long as you model your system mathematically so that outgoing speeds compensate for whatever you chose on the inward direction, so that the round trip time equals the time we actually measure, the two-way speed. So you're free to model the universe mathematically so that light gets here infinitely fast, as long as you say that it goes back out at twice c, the constant in physics representing the speed of light, so that the total round trip time is what you would expect from an average of c. How many people did I just lose in that last couple sentences? A lot of you. One-way speed of light, speed in only one direction, can never be measured. It's not a question of needing better technology, it's a question of it being impossible to ever do, period, according to relativity and according to Einstein himself. Einstein said if you have a problem with, if you have a situation, a calculation where there's light traveling in only one direction, you can choose whatever speed of light you want to solve your situation. As long as you model things consistently so that light traveling in a round trip will come out to be 186,000 miles per second over the whole distance. I know this is a hard idea to grasp, and I'm still trying to come up with examples as to how to explain all this. But the important part is Einstein himself admitted one-way speed of light can never be measured. It can never be known. In a sense, it's even improper to ask the question, because when you're modeling your problem mathematically, you're free to pick whatever number is most convenient for you in that situation. This means that the one-way speed of light ultimately is arbitrary. You can stipulate whatever one-way speed you want, depending on the problem you're trying to solve. But the LTT issue requires this number to be absolute, not arbitrary. So if the LTT issue relies on an equation which assumes the one-way speed of light is an absolute, never-changing number, but relativity itself says it's an arbitrary choice, not an absolute number, that means LTT is not a valid challenge. So this isn't actually a solution to the problem so much as it is an invalidation. It's pointing out that the problem itself is invalid because it requires something to be absolute that is not absolute. Okay, that one was tough, I know. So let's move on to some easier ones. Assumption 4, that the speed of light is constant through space. Again, we're focusing on the speed aspect of this equation. You can look up on Wikipedia or a book or whatever what the speed of light is. And again, it's 186,000 miles per second, whatever. But where have we ever measured the speed of light? Where have all of our measurements, all through history, been done? Within the solar system. Because we've never been outside of our solar system. There's a couple of spacecraft on the edge of it now, but that's it. Every measurement of speed of light we've ever done has been done within our solar system. What is the speed of light outside of our solar system? We don't know. We've never measured it. Is it possible that maybe in interstellar space in between the stars, if light isn't being affected as much by, for example, our sun's gravity, that it's different? Within the solar system, we're heavily influenced by the gravitational field of our sun, right? Well, what if light was affected by gravity somehow? So that the farther outside of a gravitational field you get, the faster light might travel. Then between the stars, it would travel more quickly, wouldn't it? What about deep space, in between galaxies? What if you're far away from any star? Could light travel more quickly out there? We don't know. We've never measured it. We've never been out there to measure it. We assume that it's the same, but that's only an assumption. There are some people I'm aware of that are actually looking into this question. They're investigating what would be the implications of light traveling more quickly through deep space than what we've ever measured here in the solar system. Now, first of all, that would obviously change this LTT calculation, wouldn't it? If light could travel a lot more quickly through deep space, then it would get here in a much shorter time than a straightforward calculation would indicate, wouldn't it? Now, I'm not saying this is the case. I'm just pointing out that this is an assumption that the calculation relies on. Maybe this assumption will turn out to be correct. Or maybe not. It is yet an assumption that's still being investigated. Assumption 5, that light always traveled the entire distance. Now back to our equation. Now we're not focusing on speed anymore. Let's question the distances involved. What if the Lord created the light in transit, created the light beams themselves in place, as it were? This idea is based on the fact that the Lord had to create at least some of the initial creation mature. Did Adam wake up next to a pile of pits and seeds, or did he wake up next to mature fruit trees? Well, mature fruit trees, right? For that matter, did Adam wake up as an infant or a man? Or for that matter, an embryo? Well, obviously he was mature, the trees were mature, his environment was mature. So it's necessary that at least some of the creation was mature from the very beginning. What if that includes the stars and the light in between those and us? Well, some people have a problem with this idea. Here's an example of a problem that some people have. This is the supernova that was seen in 1987, thus the name, 1987A. And this little bit directly in the middle of that larger photograph is what this here is showing you. Now, we saw this thing blow up. It was a star. We saw a star, and then we saw an explosion. And today, it looks like what we see in the upper right there, these expanding rings of gas. And we're watching it change as the years go by, and we're learning lots of cool stuff about how supernovas and their remnants change like this. But this supernova was 168,000 light years from us, give or take. So, if the Lord created a light beam in between us and this thing out there, what was in that light beam? Well, since this explosion happened almost 6,000 years after creation, let's call it 6,000 to make it easy, that means you had this light beam that's 168,000 light years long. The first 6,000 light years contained the image of a star. Then there was an image of an explosion, the supernova. Subsequent to that, there's been a number of years where that part of the light beam contained these images of the expanding gas rings. Point is, we saw a star where there never actually was a star on the far end of that light beam, according to the mature creation idea. Some people have a problem with that. They think that if God had done it that way, it would make him deceptive, because he would be showing us things that never actually existed. I understand the concern there. I personally don't think that would be deceptive, because the Lord told us how he created things. Adam wasn't deceived by the fruit trees, right? If Adam woke up to the fruit trees that looked about 5 years old, he wasn't deceived by them because God told him, oh, I made these just 3 days ago. Similar fashion here, if the Lord tells us when he made the cosmos, we shouldn't be deceived if we're trying to interpret things differently than what he said. Moreover, most people would admit that the earth had to be created in a mature fashion, but they would say nothing else outside of the earth. But I would say, well, the question of whether or not stars are created mature, at least one star had to be created mature initially, and that's our sun. Nuclear fusion deep within the sun produces photons. Photons arrive here as sunlight, but they don't do that right away. Photons, according to our understanding of stellar physics, take thousands of years to work their way toward the sun's surface. Once they reach the surface, they then shoot to us at the speed of light in a little over 8 minutes. But they're trapped in the sun for thousands of years first. Could Adam see the sun when he first awoke? I think we'd all say yes. Well, that means God had to create that sunlight in transit. He had to create that beam of light as it is, because the sun itself was not producing light in a way that it would get to him yet. Could Adam have analyzed that light with a spectrometer and all the rest of it to see things within the light beam? Yes. Was he being deceived by an apparent history that's not true? No, because the Lord told him when he had made everything. So I think we have to include at least some of the mature creation aspects in our creation models. I'm not necessarily saying that all the light beams were created all the way out, but I think it deserves a bigger spot at the table for our creation cosmologies than what some people are willing to grant it. But my point for this evening is that is an assumption that the LTT issue is based on, that the light had to travel all the way from that object to here. And that's not necessarily true. Assumption 6, that light always traveled as it does today. Again, back to our equation. This time we're challenging speed again. Genesis has some interesting things to say in some places. Genesis 1 says that God said, let the earth bring forth grass and seeds and the fruit tree yielding fruit after its kind and so on. And the earth then went ahead and brought forth grass. Sometimes we tend to think that during creation God said, let there be plants, zap, and there was plants. But that's not actually what Genesis says. Genesis says that God said, let the earth bring forth the plants. And then the earth did that. The word in Hebrew here is dasha, the word for bring forth. It implies here that there was an accelerated process going on right out of the gate there at creation. God didn't just say, zap, there's the earth, there's the universe. He said, let the earth bring forth these things. And so it seems that what we would think of as a normal process of the earth bringing these things forth happened, but during a very short period of time, an accelerated time. Could this also apply to starlight? When the Lord created the cosmos, could he say, let the stars bring forth light and accelerate their travel to here? Well, sure, he could do that. And Scripture doesn't say directly that he did do that, but the use of the word dasha is very intriguing. If it applied across the creation, then that also would address the LTT issue, wouldn't it? Now, some people say, well, wait a minute, you're explicitly invoking a miracle here, though. God creates the stars and then supernaturally accelerates the light on the way to us. Well, yes, it is explicitly miraculous, but so is the creation itself. I mean, you go far enough back in time, you're going to be at a miracle at one point or another, right? Moreover, unless you're going to invoke something outside of the natural laws of physics, you can't explain the universe to begin with. So the existence of the universe itself is miraculous. So we shouldn't shy away then from acknowledging that maybe some supernatural processes were at play even a few days into creation week. So assumption 6, light always travels as it does today. That's not necessarily valid. It is merely an assumption. Assumption 7 is that the universe had no center of mass and has no center of mass. Now back to our equation, but this time we're not talking about speed, we're not talking about distance. Instead, we're talking about time itself. Why is it important, this whole issue of the universe having a center of mass? Well, it's interesting because earlier I told you about redshifts, and that redshifts are usually interpreted as evidence of motion, and that with the exception of a few things close to us that are moving toward us, everything else we see is moving away from us. And the farther out we look, the faster everything's traveling. I told you that that's also the fundamental discovery that was responsible for the Big Bang model being formulated. But the Big Bang model is not the only possible interpretation of these redshifts. When we look out into the cosmos, we see redshifts in all directions. We see an expanding universe, and it appears that we're at the center of the expansion. So there's two possibilities here. Number one is, we appear to be at the center of an expanding universe because it would look that way from anywhere or from everywhere. So this Big Bang interpretation that I told you about, notice the very top diagram there, everything is farther away from everything else. So regardless of which galaxy you started in that middle, as time progressed, you would see all the others moving away from you. That's how the Big Bangers interpret, that's how secular cosmologists interpret these redshifts. But that's not the only possible interpretation. Here's the second one. We appear to be at the center of an expanding universe because we are at the center of an expanding universe. That fits the observations just as well as the way that the secular cosmological community interprets it. Why do they make that choice? Why do they insist that option 1 is the correct choice and option 2 is off the table? Here's Edwin Hubble, who was one of the pioneers in discovering redshifts and their relationship. Hubble was very clear about what he thought about us being at the center of an expanding universe. He said the unwelcome supposition of a favored location must be avoided at all costs. A favored position, of course, is intolerable. Therefore, in order to restore homogeneity and to escape the horror of a unique position, the departures from uniformity must be compensated. There appears to be no other escape. Hubble recognized if we're at the center of an expanding universe, that has some implications. Number one, it means the universe has a very special place, the center. And number two, we appear to be there. What does that make us? Special. What did he think of that idea? It's unwelcome. It's to be avoided at all costs. We need to escape the horror of a unique position. The horror of maybe being special, because that would imply there's a creator. He continued, if we see the nebulae all receding from our position in space, then every other observer, no matter where he may be located, will see the nebulae all receding from his position. However, the assumption is adopted. So that's the assumption that the Big Bang model is based on. There must be no favored location in the universe, no center, no boundary. All must see the universe alike. This assumption is at the very foundation of the Big Bang model. This idea that the universe can have no center. In fact, you have to decide if the universe has a center before you can even apply math and make a cosmological model. Because you take the observed redshifts, the idea that everything's moving away, you apply the cosmological principle to that to say that there is no center, therefore any observer would see similar things no matter where he was, and then you apply the mathematics of general relativity to it. That's the foundation of the Big Bang model. So this cosmological principle, this denial that the universe can have a center, is at the very foundation of the Big Bang model. And a lot of Christians don't realize this. You frequently see comments from people saying, oh, we need to embrace the Big Bang model because it shows that the universe had a beginning, and that's good for us. Well, first of all, you don't need the Big Bang model to prove the universe had a beginning. Remember the cup of coffee analogy? Go outside, do you see stars? Yes. That proves the universe had a beginning, that it's not eternal. So you don't need the Big Bang model for that. But point two, the Big Bang model is based on an anti-theistic assumption, isn't it? It's based on a denial of us possibly being at a favored location in the universe. The horror of a unique position, according to Hubble. So people want to embrace a model that at its core has an anti-God assumption built into it. And this is just an assumption. This is the point I'm emphasizing now. This principle that the universe has no center, that's not an observation. It's an assumption. Moreover, it's an apparently invalid assumption, because the redshifts plus the assumption plus general relativity equals the Big Bang model, which violates physics. So if your conclusion is wrong, you got to go back through and see what assumptions went into it. Well, the redshifts, we see those. Relativity is good physics. That means this assumption must be the part that's wrong. Okay, so why is this relevant to LTT? If we appear to be at the center of an expanding universe because we actually are at the center of an expanding universe, well, that has some implications. If there's a center of the universe, then there could be a center of mass to the universe. And that brings in the possibility of time dilation early in the universe's history. What is time dilation? Well, this is an implication of general relativity. Relativity says, among other things, gravity affects time. We have several atomic cesium clocks here in the U.S., and this prediction of relativity is actually verified by the operation of these clocks. We have one at sea level on the East Coast, for example, and one at roughly a mile above sea level in Colorado. The one down at sea level ticks. Atomic clocks don't tick, but this one ticks, quote unquote, a little bit more slowly than the one a mile above sea level. Why is that? Because the one at sea level is a mile deeper in the Earth's gravitational well than the one a mile above sea level. That difference was actually predicted by Einstein and shown to be true. I'm showing you on the slide here a picture of the GPS system. I actually got to work on the GPS a little bit. I got to see the design documentation because I was working with the folks who flew those things. And the GPS engineers had to compensate for this effect in their design of these satellites. Why is that? GPS requires very tight calibration of the clocks on the satellites to the clocks down here in our receivers. And time flows a little more quickly up there in orbit than it does down here on the surface, because we're deeper in the Earth's gravitational well. Again, gravity slows time down for us slightly. They have to compensate for this. If the satellites didn't compensate for this difference, they would actually slowly drift over time in terms of their calibration, and it would stop working. Okay, why is this important? Because of verses like this. Thus says God the Lord, he that created the heavens and stretched them out. A number of years ago, a Bible-believing physicist was reading either this verse or one of the other ones that say similar things, and said, what if that's not just poetry? What if that's literal? What if God created the entire universe in a small volume of matter, a small sphere? Well, if that sphere was small enough, then the initial universe would have been in a black hole. And I'm showing you on this little diagram here, the dotted line represents the event horizon of the black hole. Now, event horizon is not a thing, it's just a distance. It's the distance within which the black hole effects are operating. Now, because gravity affects time, time within a black hole is almost stopped relative to outside the black hole. But that didn't matter here because the entire universe was inside at first. But now God starts stretching. That means the universe gets bigger, the volume gets larger, which means the density gets smaller, which means the black hole gets weaker, which means the event horizon moves inward. And now God starts creating things from the matter. This is still within creation week. God continues stretching. Eventually you reach a time when the universe is large enough and the black hole small enough that some of the universe has moved outside of the boundary of the black hole. And now's where it gets interesting, because now you have some of the universe outside the black hole. So time starts flowing normally for it, for that matter, for those locations. Whereas time inside the black hole is still almost stopped. And the Earth is somewhere near the middle of this, which is consistent with the observations that we see, right? We appear to be at the center of an expanding universe. So God continues stretching. Universe gets bigger, black hole gets smaller. More and more of the universe now is in a region where it's not affected by the black hole anymore. So time is flowing normally out there. More time is passing out there, whereas time here is still basically stopped. God continues stretching. Eventually, the universe gets large enough that the density gets low enough that the black hole goes away. From this point on, which is where we are today now, clocks throughout the universe are ticking at the same rate because time is flowing at the same rate everywhere, except for local differences like being next to a star or a planet or something. But what has happened before this point? Lots and lots of time passed out there, whereas very little time passed in here because we were inside the black hole for most of that creation period. So you could have millions or billions of years register on a clock out there, while a clock here would register 6 24-hour days. So if you ask the physicist who came up with this idea, how old is the universe? He would say, according to which clock? Because which of these clocks is correct? They all are. They all accurately measured how much time flowed in their local region, depending on how the mass of the universe was distributed. So secular cosmologists assume that the universe has no center of mass, because otherwise they'd be forced to say that we're at the center of an expanding universe, which would make us very special, and who put us here anyway? Since they don't like the answer to that question, they deny that there is a center at all, and that's how their math continues from there. We're under no obligation to make this anti-theistic assumption, though. We can say, well, the observations make it look like we're at the center of an expanding universe. Maybe that's because we are at the center. Well, that would mean that there was a center of mass early in the universe's history. That would mean, depending on how it was initially configured, you could have this time dilation happening very early on in creation. And so the LTT issue is explained easily. So the question of, does distant starlight disprove biblical creation? Hopefully I've made the point that the answer is no. The question itself relies on a whole series of assumptions. At least some of those assumptions are wrong. Some of the others are questionable. And by challenging some of these assumptions, we're actually coming up with multiple possible solutions for this question and multiple possible creation cosmologies. So it is now the exciting work to investigate these things further and see if we can learn more about how the Lord actually made the cosmos we see. Because the universe does not declare that there was a Big Bang. The universe declares the glory of its creator. I have an email newsletter that's available to you if you like to get more of this perspective on astronomy. I think it's probably obvious you won't get this from PBS or NPR or whatever, right? That's available on my website, which I'll show you in a minute. I also have several videos, which I will not take the time to describe in depth here. I know some of you have them already. If you are not familiar with these, you will find them on the book table back here. Again, presenting things on astronomy that you will not typically hear from the secular perspective, the science museums and all the rest of it. Because the heavens declare the glory of God, not 14 billion years history of a Big Bang. This is my site. The email newsletter is available to you, and that brings my presentation to a close. Thank you very much for your attention.
All right, thanks a bunch, Spike. We're going to take up a quick offering. We're responsible for our speaker honorarium, so please dig deep and help us out. Make checks out to Cedar Park. This all gets turned over to Cedar Park, and then we do our check request when we need them. So let me just offer up a word of prayer. We can take maybe one or two questions. We're pretty much at the end of our time, but while the plates are being passed, we can take one or two questions. Let me just send our offering up with some prayer. Father, thank you much for Spike this evening, Father, and just help us absorb this information and give us the wisdom necessary to incorporate this into our own witness and testimony. Father, we ask for blessings for the offering that's taken up this evening, and that money will be used for the furtherance of your ministry, Father. We ask for your blessings upon Cedar Park. In Christ's name we ask all things. Amen. Okay, so while the plates are passing, we can take one or two questions, but we got to limit it to just a couple because they really want us finishing on time. So let me run back here. I see Bill's got his hand up. Just a second.
Hi, gravitational lensing, where there's an object in between us and the object, there's some kind of a gravitational lens, either a galaxy, and gravity is bending the light rays, so we see the object as 4 instead of 1. Is that kind of proof that gravity in some way does affect light? Maybe not in speed, but somehow gravitational lensing proves that gravity acts on the light coming from that object?
It would usually be stated a bit differently. Gravity distorts space, and then the light travels through distorted space, and so its path gets bent. So that's well understood. The question is not a matter of light traveling through distorted space, because obviously it does. The question is it going to travel more quickly through space? So a separate issue, but an excellent question. Yes, sir.
I think I read in sci-fi literature about folding space, how space travel can go further distances or faster than the speed of light by folding space. Does that make any sense?
Right. People have played with Einstein's equations to see what would be allowed. So they talk about wormholes and tesseracts and all these ways to tunnel through space or fold space on itself. That's all purely speculation at this point. We have no evidence that such would be possible. People are tending to say, well, the equations don't say it, they don't disallow that possibility, so maybe those things are real. So, yeah, it makes a good novel, right? Yes?
Do you have a favorite amongst all those different possibilities? And is there any movement in secular cosmology relative to this whole question? Anything coming down the pike?
Yes. Yes to both questions. I carefully avoided endorsing any of the particular suggestions I discussed. I like time dilation for several reasons. I think it provides a lot more opportunities for us to explain certain things. Your second question about the secular community, there's a not insignificant number of secular cosmologists who are investigating variable speed of light themselves. So they are trying to come up with their explanation of how light speed could have changed in history, in part to explain some of the problems that it poses for them. This is something that doesn't get a whole lot of attention, but it is out there. So I obviously don't know how big of a movement it's going to turn out to be, but I think it's interesting that even the secular folks are raising that as a possibility and trying to invoke it to solve some problems. So, for us to make some of the suggestions we're making, if they can do it, we can do it, I guess is what I'm saying.
So
Yes, sir.
you said that your favorite is time dilation, which would be the last one that you talked about, correct?
Yes.
Okay, so what does this do for this? It says in Genesis chapter 1 that there's waters above, waters below.
Right.
And I've seen models where they do this time dilation, the waters above are at the extreme edge of creation.
Yes.
However, I interpret the waters above as falling when Noah in his ark, the waters from above, I interpret that layer of water being what comes down from above. Is that an incorrect interpretation? And would those waters still be existent out there someplace?
What are the waters above is the question. Genesis talks about them being above the rakia. Rakia is the word that's often translated firmament, and that's not really a good translation, but why that happened we don't need to worry about. If you look at rakia, it talks about more than just the sky, more than just our local atmosphere or whatever. Rakia would apparently extend deep into space because it talks about the stars being in the rakia, for example. So I think the waters above were, as one of the things you mentioned, actually a shell of water in whatever form on the edge of the universe, and then that would have expanded as the universe did. And so, yeah, I think it's still out there. It's one of the possible explanations for the cosmic microwave background, by the way, among other things. So, and that shell of water, that shell of mass being there also has implications for how the time dilation happened. The time dilation model I included here, by the way, has been developed further by the physicist who came up with this idea. And his later work includes the waters above as an outer boundary for the universe. And that changes what happened on the inside a bit, but that would get more complicated and take more time than I had. So thank you for the question.
Was that Russell Humphreys? Seemed like he was
Correct,
the one
yes.
first. Yeah.
Dr. Russell Humphreys.
Good stuff, right? You guys thank
you.
Spike one more time. Oh,
Okay, thank
that's
you.
Good stuff. Appreciate it. So we want to close this out briefly, but just remember, next week I'm up doing a talk that I've titled "The Wonders of Creation." So just come out just to learn about some of the amazing design features, cosmological design, biological design, everything that's out there just declares the glory of God. So it should be good. Spike, would you close out in a word of prayer, please?
Yes. Heavenly Father, we thank you, Lord, for the opportunity to gather here and to discuss what you have done, Father. In your mercy, Lord, you've given us glimpses of what you've done and the opportunity to glorify you through them. Just help us, Lord, to do so. Help us to perceive more of your glory. Help us to worship you in all of your wonder and splendor. Just thank you again in the name of your Son, for whom you provided atonement. Amen.